Okay, so Bismillah Rahman Rahim. We were discussing the irrigation efficiencies. So, efficiency is the ratio of water output to the water input, and objective of efficiency concept is to show when improvements can be made which will result in more efficient irrigation. So for these efficiencies, we will define water conveyance efficiency, water application efficiency, water use efficiency, water storage efficiency, water distribution efficiency. So first we define water conveyance efficiency. It is the ratio of water delivered to the farm or irrigation plot to the water supplied or diverted from the river or reservoir. It is given by this expression where eta C, that is the water conveyance efficiency, WF is the water delivered to the farm or irrigation plot, and W with a subscript R, that is water supplied or diverted from the river or reservoir. So the water that is supplied or diverted from the reservoir or river, and then the water that is delivered to the farm. So this account for the losses, that is the water conveyance losses. We convey the water to the through network of irrigation canals. So definitely there will be losses. So this water conveyance efficiency, it considers those conveyance losses. Next we have water application efficiency. It is the ratio of quantity of water stored into the root zone of the crops to the quantity of water delivered to the field. It focuses the attention of the suitability of the method of application of water to the crops. So water application efficiency, that is the water delivered to the field and the water that is stored into the root zone of the crops. So the ratio of quantity of water stored into the root zone of the crops to the quantity of water delivered to the field. It is mathematically given by this expression where eta A is the water application efficiency and W sub S is the water stored in the root zone during irrigation, and W sub F, that is water delivered to the farm or irrigation plot. The common sources of loss of irrigation water during water application are the surface runoff from the farm and deep percolation below the farm root zone soil. So WF is equal to WS, that is water stored in the root zone, plus RF plus a DF. RF is the runoff from the farm and DF is the deep percolation below the farm. So it means that WS, that is the water stored in the root zone, that can also be written as WF minus RF minus DF. So it means that this can also be written as this eta A this WS can be written as WF minus RF minus DF divided by WF into 100. Next, we have water use efficiency. It is the ratio of water beneficially used, including leaching water, to the quantity of water delivered. Mathematically, it is given by this expression where eta U is the water use efficiency, W sub U is the water used beneficially or consumptively, and W sub D, that is the water delivered. Water storage efficiency. It is the ratio of the quantity of water stored in the root zone during irrigation to the water needed in the root zone before irrigation, prior to irrigation. So it is given by this expression eta S, that is the water storage efficiency. W sub S is the water stored in the root zone during irrigation, and Wn water needed in the root zone prior to irrigation, before irrigation. So this is how we define the water storage efficiency. Water distribution efficiency. Water distribution efficiency evaluates the degree to which water is uniformly distributed throughout the root zone. Water distribution efficiency evaluates the degree to which water is uniformly distributed throughout the root zone. The more uniformly the water is distributed, the better will be the crop response. So it is given by this expression here, where eta D is the water distribution efficiency, Y is the average numerical deviation in depth of water stored from average depth stored during irrigation. So if there is no deviation, so then what will happen? That this will be 0, Y will be 0. So the water distribution efficiency, that will be 100%. So this Y is the deviation from the average depth of water stored during irrigation. This Y represents the average numerical deviation. So if there is no deviation, then this Y will be 0. 1 minus 0, then this efficiency will be 100%. Next, we define a few terms. We have gross command area. So the gross command area is the total area bounded within the irrigation boundary of the project that can be irrigated economically without bothering about the limitation of quantity of water available. So what is the gross command area? It is the total area bounded within the irrigation boundary of the project that can be economically irrigated without any limitation of quantity of water available. The gross command area. The gross command area includes the cultivable area that can be cultivated and uncultivable area. The examples of the uncultivable area include ponds, residential areas, reserved forests, and roads, etc. So the gross command area includes both cultivable area and uncultivable area. Cultivable area, that is cultivated for crops, and uncultivable area, the examples are, we have other areas on the land. So for example, we have small ponds, residential areas, roads, reserved forest, etc. A doab is an area between two drainages. Doaba. This is a common word that we studied in Pak studies, maybe at the school level. A doab is area between two drainages. When a canal system lies on a doab, the irrigation is economical. Here, the gross command area is the area enclosed by the drainages on both the sides, and hence gross command area forms the geographical area of the doab. So you can see here we have this river here. This is the river flowing. Then we have these drainage that drains into the river. You can see here from this river we have diversion head work that we will study in detail in the coming lectures. So we raise the water level, and then we have the canal head regulator that we regulate the flow of water into the canal. So this is the canal. This is the main canal. You can see here, this is the main canal. And then from the main canal, we have the branch canal. So this is the branch canal. This is the branch canal, and so on. We will study in detail about the canals also and their design, diversion head works, canal head regulator. So you can see here that we have cultivable area that can be cultivated for the crops, and we have unculturable area that could include the residential areas, water ponds, etc. So the gross command area is this bounded by the dash line here. This is the gross command area. So it includes the culturable area as well as the unculturable area. Cultivable command area. Gross commanded area contains some unfertile barren land, local ponds, villages, etc., which are actually unculturable areas. The gross commanded area minus these unculturable areas on which crops can be grown satisfactorily is known as the culturable command area. So the gross command area minus these unculturable areas on which crops can be grown satisfactorily is known as the culturable command area. So culturable command area, that is the gross command area minus unculturable area. Culturable cultivated area, the area on which crop is grown at a particular time or crop season. Culturable uncultivated area, the area on which no crop is grown at a particular time or crop season. And the reason here is that sometimes we leave the land, one crop is grown, and then at other time it is left as uncultivated, no crop is grown for different purposes. The reason could be to improve its productivity, etc. Let us try to solve another problem. We have an irrigation canal, has a gross commanded area of 80,000 hectares, out of which 85% is culturable irrigable. The intensity of irrigation for Kharif season is 30% and for Rabi season is 60%. Find the discharge required at the head of canal if the duty at its head is 800 hectares per cubic for Kharif season and 1700 hectares per cubic for Rabi season. So we want to calculate the discharge that is required at the head of the canal, the water that we need to release. So let us try to solve this problem. Now in this case, the cultivable irrigable area, you can see here gross commanded area is 80,000 hectares, out of which 85% is cultivable irrigable. So we have this cultivable irrigable area. This will be equal to 0.85. This is 85%. So we have this is 85 divided by 100, 0.85 multiply by this 80,000. So this is equal to 68,000 hectares. Now area under Kharif season. So we have area under Kharif season. That will be equal to how much? The intensity of irrigation, it means the area that has to be irrigated for Kharif season is 30%. So this will be equal to 30 divided by 100 or 0.3. This is now the cultivable irrigated area 68,000 hectares. So this is multiplied with 68,000. So this is equal to 20,400 20,400 hectares. Similarly, we have area under Rabi season. So we have area under Rabi season, winter season. So that will be equal to how much? we have 60% here. So this will be equal to 60 by 100. Multiply by 68,000. So this is equal to 40,800 hectares. Now what we have is that we want to calculate the water required at the head of canal for the 2 seasons, because you can see here the duty that is different here. The duty at its head is 800 hectares per cubic for Kharif season and 1700 hectares per cubic cubic means cubic meter per second, clear? Hectare 10 power 4 square meter for Rabi season. So we want to calculate the water required now. So we have water required at the head of canal, at head of canal for Kharif season. So that will be how much? We have the total area here under Kharif season, that is 20,400 hectares. So this will be equal to 20,400 hectares divided by what is the duty here. So the duty for Kharif season, that is 800 hectares per cubic. We have 800 hectares per cubic. So now you can see this hectare cancel out, this cubic will go up. So we will get this here 25.5 cubics. 25.5 cubics. So this cubics is actually cubic meter per second. Similarly, we have water required for Rabi season. at head of canal where the water enters into canal, head of canal. So we have for Rabi season, so what is the area for Rabi season? That is 40,800. So that is 40,800. And what is the duty? 1700 hectares per cubic for Rabi season. 1700 hectares per cubic. We have this as in hectares also. So this is equal to 24 cubics. Thus, the water required during Kharif is more than that in Rabi. Hence, canal must be designed to carry a discharge of 25.5 cubics. So, canal must be designed for 25.5 cubics. Now, actually, the canal must be designed to carry the peak discharge. Actually, it should be designed to carry the peak discharge, because here these values that we are assuming, these are the average values. So we have the calculated this 25.5. This is the average discharge calculated based on the average duty figures which are given here. So actually, canal should be designed for peak discharge. Now, in the literature, they say that this peak discharge this can be taken as 20 to 25%, 20 to 25% higher than average requirement. Higher than average requirement. So this is how we can calculate, find the discharge required at the head of canal if the duty at its head is 800 hectares per cubic for Kharif season and 1700 hectares per cubic for Rabi season. Next, we solve another problem, the base period intensity of irrigation. So this is the base period for the crops. Intensity of irrigation, that is the area under the crop that is given, and duty of various crops, duty at the field hectares per cubic under a canal system are given in the table below. Find the reservoir capacity if the canal losses are 20% and reservoir losses are 12%. So this reservoir losses, it can be evaporation losses, it can be seepage losses. Similarly, from the canal losses can be evaporation losses and can be seepage losses. Clear? So how to solve this problem here? You can see that we are given the crop. Then we have the base period, so that is denoted by B, days. Then we have duty, of water, so that we denote by D. Now this is hectare, this is given in days, this is given hectare per cubic per cubic. So we have this is hectare, units are very important, hectare per cubic. Now we are given the area for each crop. That is also given in hectares. So this is actually given for us. Now we have wheat. Then we have sugar cane. Then we have cotton. Then we have rice. And we have vegetable. Now for this, it is given here 120, 360, the number of days are given for this. here for all the crops. So we have 120 here. Then we have 360. Days for sugar cane. So you can see that sugar cane is actually a year crop. It means that when we grow sugar cane on land, we will not be able to grow any other crop for the rest of the time. You can see 360 base period. This could be the reason why you see that in this Peshawar area, so sugar cane production has significantly reduced. This could be the reason. Now cotton we have 200. The rice B days is 120. And for vegetable again we have 120. Now the duty, that is 1800 for wheat. Then we have 800 for sugar cane. Then we have 1400 for cotton. For rice it is 900. And we have 700 for vegetable. Now the areas that are given here, 4800 area under the crop here, 4800. Then we have 5600. (4800), 5600. Then we have 2400. Then we have 3200. And we have 1400. Now what we can do is that here we can calculate the delta. We want to calculate the reservoir capacity. We want to calculate the total volume of water that is required. So the delta in this system of units, that will be equal to 8.64 as we discussed in the previous lecture, into B by D, where B is the base period and D is the duty. And here the units are meter. So it means 8.64 multiplied by B by D. So you can see for the crops B and D are given, we can calculate this delta. So this will be equal to 0.576. Then for sugar cane, it is 3.890. Then for cotton, 1.234. For rice, it is 1.152. And for vegetable, it is 1. This is the delta in meter, the depth of water required for this entire crop period for these crops, 1.481. Now we need the volume. So we have this area here. This is in hectares. You can see this is the area under the crop in hectares. So this area, because we have to irrigate this area, so area multiplied by the depth, delta. So we can calculate the volume. So volume, that will be equal to delta, and this is the area. So delta multiplied by the area. So this will be, area is in hectares and delta is in meter. So what will be the units here? The units will be hectare meter. So just we need to multiply this delta with this area A. So this will be equal to 2765 hectare meter for the wheat crop. Then for sugar cane, this will be equal to 21784. For cotton, it will be equal to 2962. For rice, it will be equal to 3686. And for vegetable, it will be equal to 2073. Now we need the total volume, because you see that the question asks find the reservoir capacity. So now we have to add all this. We need the total volume here. So this will be equal to 33,270. 33,270. Now it is given that if the canal losses are 20% and reservoir losses are 12%. So capacity of a reservoir, we can write down here, capacity of a reservoir this is the volume here, 3327, and then divided by, we have canal losses is 20%, so we have to divide this by 0.8. We have to divide this by 0.8. And then the reservoir losses are 12%. So again, we have to divide this by 0.88. By this much we have to increase. Clear? You divide this by 0.8. Actually, this 0.8, it comes 1 minus 0.2. So this is equal to 0.8. So you divide this by 1 minus 0.2, or you divide it by 0.8. We have the same. It is like this. Similarly for the 12% losses. So this will be equal to 47,258.52 hectares. Hectares meter. Let us write down small h to be consistent. So this is the capacity of the reservoir. Now we briefly discuss about the quality of irrigation water. So a good irrigation water is the one which performs the required functions without any side effects which retard the plant growth. You studied about the quality of water in detail and the different tests that we conduct, the physical, chemical, biological. So the same concept apply here, but we have to see that is the water fit for crops or not. Irrigation water may be said to be unsatisfactory for the intended use if it contains chemicals toxic to plants or the person using plant as food. Chemicals which react with the soil to produce unsatisfactory moisture characteristics, and bacteria injurious to person or animals eating plants irrigated with the water. So irrigation water may contain various types of salts such as sodium, calcium, magnesium, and potassium, etc. A high concentration of these salts may prove to be injurious to the crops. The water quality for irrigation is determined by three approaches. We have salt concentration, electrical conductivity, and we have sodium absorption ratio, SAR. Salt concentration. The salt concentration is generally expressed by ppm, parts per million, or milligram per liter. However, amounts in excess of 700 ppm are harmful to some plants, and more than 2000 ppm is injurious to all crops. Electrical conductivity, these are the guidelines. So between the different sources, if you study irrigation books or other literature, these values can slightly vary depending upon the standards for which you follow. Just like you studied in environmental engineering, you have the drinking water, you have the WHO guidelines. Then for Pakistan, we have our own guidelines that may be slightly different or similar. So that's why these are just a guideline values given here. They may be slightly different from source to source. Electrical conductivity, the salt concentration is also measured by determining the electrical conductivity of water and is expressed in micromoles per centimeter. Low salinity water, the value up to 250 micromoles per centimeter is called as low conductivity water, can be used for irrigation. Medium salinity water, the value from 250 to 750 micromoles per centimeter is called as medium conductivity water, can be used for irrigation for normal salt tolerant plants such as, for example, cotton, alfalfa, cereal, grain, sorghum, etc. Then we have high salinity water. The value from 750 to 2250 micromoles per centimeter is called high conductivity water. Can be used for high salt tolerant crops with proper drainage. For example, barley and oat. Very high salinity water, the value above 2250 micromoles per centimeter is termed as very high conductivity water. It is not suitable for irrigation. The third one is the sodium absorption ratio, commonly called SAR. The proportion of sodium ions present in soil is generally measured by SAR, which is mathematically given by this expression. The sodium and the calcium, magnesium ions that we have. So this gives us the SAR, sodium absorption ratio. We have low sodium water. When the value of SAR lies between 0 to 10, it is suitable for all crops except those which are highly sensitive to sodium. Medium sodium water, when the value of SAR lies between 10 to 18, may be used on coarse textured or organic permeable soils. Addition of gypsum either to water or soil is required for use on fine textured soils. The soils tend towards alkaline because of increase in pH value. So these are the different categories, and we calculate the SAR accordingly. We have to treat the soil, or I add gypsum, for example, here to the water. High sodium water, when the value of SAR lies between 18 to 26, may be used provided gypsum is added and good drainage and high leaching is provided. Very high sodium water, when the value of SAR is above 26, generally not suitable for irrigation. So again, these are the guideline values, can vary from source to source, book to book, but here the purpose is just to give some guideline values to assess the quality of irrigation water. Next, we also have boron toxicity. Boron is essential to the normal growth of all plants, but the amount required is low. If it exceeds a certain level of tolerance, depending on the crop, then boron may cause injury to the crops. So this is a guideline given that we have class low, boron content milligram per liter below 1, suitability for irrigation, so it is excellent. Medium class 1 to 2 milligram per liter, suitable for most crops. High 2 to 4 for more boron tolerant crops. Very high, that is above 4, so should not be used for irrigation. Similarly, we have the chloride toxicity. So the most common crop toxicity is caused by chlorides in irrigation water. The chloride anion occurs in all waters. Chlorides are soluble and leach readily to drainage water. Chlorides are necessary for plant growth, though in high concentrations they can inhibit, that is restrain, plant growth and can be highly toxic to some plant species. These are the guideline values for the chloride concentration, milli equivalent per liter or parts per million. So you can see less than 70 parts per million generally safe for all plants. 70 to 40 parts per million sensitive plants usually show slight to moderate injury if chloride is present. 70 to 140 parts per million in the water. 141 to 350 parts per million moderately tolerant plants usually show slight to substantial injury, and if the chloride concentration is more than 350 parts per million can cause severe problems.